Hello and welcome to GigaSpaces XAP 10 MemoryXtend screencast. My name is Shai Hasidim, GigaSpaces Deputy CTO. The agenda for today includes an overview of XAP MemoryXtend. It includes a simple benchmark comparing a RAM-based data grid versus an SSD-based data grid. I'll show you how the MemoryXtend configuration looks, how you configure such a data grid. And we'll have a look at one very cool functionality of MemoryXtend that is fast data re-indexing and data recovery straight from the SSD. You don't need a database as a persistency technology anymore. What is MemoryXtend technology? It's designed to manage large amounts of data in a grid configuration using high-density SSD capacity servers. It builds on top of SanDisk's Zetascale technology, embedded within XAP. You can have a very large dataset maintained with XAP's data fabric where the actual data is maintained on SSD, not on RAM. The value you get out of it is very straightforward. Incredible server consolidation, where you can reduce up to between 60 to 80% of your data grid hardware with such technology while processing large data sets. In terms of the actual data capacity per node, we're talking about an incredible increase with the amount of data that each data grid instance may store. From a 30 gigabyte maximum, which is the average, to a 3 terabyte per data grid instance. That's an awesome increase. There are several motivating factors behind leveraging SSD technology. Offering a relatively low-cost, ultra-sized capacity data grid while reducing the amount of hardware. Obviously, the price of the SSD, which is dropping, is also an incentive, as is the maturity of SSD API, like Zetascale, that is used with XAP MemoryXtend. And lastly, lowering the dependency on databases as a persistent store for an in-memory data grid. You don't need a database to act as the persistency medium. Upon shutdown and restart of the data grid, it'll recover its data very quickly. Another very interesting functionality here is that you can leverage any flash technology, any SSD, with any hardware with XAP MemoryXtend. There's no special lock-in into a special hardware or in flash technology with MemoryXtend. You're free to use any flash technology. Let's take a look at a simple sizing example. If we'll use a standard classic HP or Cisco server, each one of these can support up to 2 terabytes of RAM. These support up to 8 SSD card slots, which means that you can have either Intel or SanDisk or Fusion I/O, which is part of SanDisk, or any other flash technology. Most of these will support up to 3 terabytes capacity and above per card. This means you can easily have 24 terabytes SSD capacity per server. With 4 servers, you can accommodate 96 terabytes total capacity. Imagine the amount of machines and money you will need to spend to accommodate such capacity with a pure RAM configuration. It will be 48 servers with 2 terabytes of RAM to accommodate such a capacity. That's an incredible amount of management, and obviously a very high cost to accommodate such a data grid environment. When looking at XAP MemoryXtend positioning, it shifts XAP technology from a classic in-memory data grid into a very important piece of technology used not only with in-memory data grids, but also within big data and real-time analytics scenarios. It can be leveraged both as enterprise caching fabric, but also in NoSQL big data, stream processing, and real-time analytics infrastructures, with or without a database backend. If we'll take a look at a typical usage scenario, we'll see that XAP can be used to manage hundreds of terabytes of data serving event streams or clients that push data, and other clients that demand fast response times. These could be mobile clients or large web applications. On the back end, the XAP technology can interact with any back-end database, whether it's relational or non-relational, SQL or NoSQL databases that are storing and managing petabytes of data with regular hard drive infrastructure. With MemoryXtend, in a scenario when you need to manipulate hundreds of terabytes, you actually don't need a back-end database for persistence. XAP MemoryXtend can be your caching and processing infrastructure, as well as your persistency infrastructure. XAP MemoryXtend offers no lock-in, neither for hardware nor storage technology. It fully supports all XAP data access routines. It supports full interoperability between Java, .NET, and C++ applications with any data model and with any data grid clustering. It comes with mature enterprise-level management technology, supporting any cloud environment. It includes advanced wear leveling implementation, prolonging the SSD lifespan, using intelligent multi-level DRAM caching. There are various durability levels supported out of the box. All core XAP functionality is supported. There's no limitation or special considerations. You can leverage all of XAP's APIs, whether it's Java, .NET, or C++, with any data modeling. Object-oriented, document schema-less modeling, SQL data access, aggregators, elastic scale, the ability to replicate data over the WAN across multiple geographies, co-located data and business logic, enterprise security and mature HTTP session replication supporting any G container. Since XAP and Cloudify are fully integrated, you can manage large-scale XAP deployments with Cloudify acting as your enterprise management tool. If we take a look at the classic local SSD architecture, you can have the SSD deployed with any server with each data grid instance, leveraging its local SSDs. The other option is a central SSD array architecture, where all the data grid instances are sharing the same central SSD array. Both of these options are fully supported. MemoryXtend configuration allows you to control two levels of LRU-based caching. One that is on heap, where you can configure it through the cache entry percentage property. And another one that is off heap, that you can configure through the blob store cache size property. Whenever data is written to the data grid, it'll be stored immediately on the SSD. Write behind option is also supported. Whenever you read data, it'll be first read from the on-heap cache. If it's not there, it'll be read from the off-heap in-process cache. And then if it's not there, only then the SSD will be accessed. Transaction and queries are fully supported. Now let's move to our demo. We have two servers running with our demo, each running a separate data grid. One data grid is a standard pure RAM-based data grid. Its entire data is stored on heap. We see it selected and monitored on the right side. The other data grid is an SSD-based data grid. It's using a Fusion I/O SSD to store its data. We see it selected and monitored on the left side of the screen. Using the benchmarking tool, we loaded 2 million space objects, 10K size each, into the RAM and SSD data grids. We can see these over here. 2 million items within each data grid. As we can see, there's a big difference between the RAM data grid configuration and the SSD data grid configuration. The RAM-based data grid consumes about 20 gig, 65% of the entire heap. The heap is configured to use 30 gig. The SSD-based data grid has an identical amount of data, but consumes less than 1 gig. You can see over here, it consumes about 2% of the heap. It stores only the indexes and some metadata on heap, and all the rest on SSD. Now let's see the performance difference running a simple benchmark comparing these two data grids. Remember, one uses RAM, on-heap data, and the other one uses SSD, off-heap data store. Our benchmark utility will be running 10 threads from a remote client where each thread will be reading a different object from the data grid. We'll see a performance difference when comparing side-by-side an SSD-based data grid to a RAM-based data grid. We can see here on the right side the real-time statistics from the RAM-based data grid. As you can see, the throughput currently measured is around 25,000 reads per second. The SSD-based data grid performs a bit slower, 17,500 reads per second. That's a minor difference when comparing the cost of each setup. Imagine 200 million items stored within the data grid. It makes a huge difference in terms of overall cost. Now let's take a look at the configuration of each data grid. The RAM-based data grid is a standard data grid. Nothing special. You can see its configuration here on the right side. The SSD-based data grid configuration displayed here on the left is a slightly modified configuration. The blob store configuration is enabled and appears here on the left side of the configuration panel. Let's take a look at the PU XML for this data grid. We've got here a new section added to the regular data grid PU XML. We see the SanDisk blob store implementation. It includes a few interesting properties. The most important one is the devices property. This is where you specify a drive or drive list that will be used to store the data for this data grid. The blob store data policy configuration used with the usual space configuration includes the cache entries percentage. Right now, we're using 1. This means that only 1% of the heap would be used to store data on heap. The blob store cache size megabyte property controls an off-heap LRU cache area that's used as second-level cache before hitting the SSD. Now, let's test data recovery and re-indexing. Our data grid runs on a single Linux machine, deployed with 4 partitions, with no backup configuration. The recovery property within the PU XML is turned on, as you can see over here. The devices are configured like this. The machine runs 4 SSD devices configured in load balancing. The SLA XML that we'll be using looks like this. Each partition is mapped to the same box. With multiple machines set up, you'll map each partition into a different machine. That's it. We've loaded 2 million items, each 10 kilobytes in size, into this data grid, and we'll test its recovery and re-indexing time. Let's redeploy it and see how long it takes to re-index these 2 million objects across these 4 partitions. We have the deployment command started. We've got here our dashboard. We'll see the deployed data grid over here. We'll monitor the log file for each GSC process hosting the partitions. We see the data grid is being deployed. The 4 partitions loading their data directly from the SSD. Each one of them eventually should have 500,000 objects. We can see the progress of the data load within the GSUI over here. As you can see, it's very, very fast. In a few seconds, we'll see the data in its entirety, fully loaded into the clustered data grid. Imagine this across multiple machines. Okay, we're done. Let's take a look at the log file for each data grid partition. We can see within each one of them the exact time it took to load these 500,000 objects. As you can see over here, it's about 38 seconds with this one, and almost the same with this one. As you can see, it's actually full parallel load process. All partitions loaded their data in the same time. All in all, it was quite fast. Almost 60,000 objects loaded per second with this setup. We can see the data over here. 2 million items within our clustered data grid. This is totally scalable, with no central bottleneck or point of failure architecture. Thanks for listening to the GigaSpaces XAP 10 MemoryXtend screencast.